Imagine pointing a telescope at a patch of sky and seeing absolutely nothing. Not because your equipment is broken, not because something is blocking the view, but because there is genuinely nothing there. No stars, no galaxies, no light of any kind. Just emptiness, stretching across 330 million light years of space. That place is real. It's called the Boötes Void, and it's one of the emptiest places in the known universe. Inside it, you'd find roughly 60 galaxies where scientists expected to find 2,000. But here's what makes this truly unsettling. The Boötes Void isn't an anomaly, it's just one of thousands. And together, these cosmic voids make up roughly 80% of everything that exists. The universe isn't mostly galaxies and stars, it's mostly nothing. And that nothing? It's hiding something that could rewrite our understanding of physics. Something that might explain why the universe is falling apart, and why we might already be living inside one of these voids right now. To understand what we're dealing with, you need to understand how empty we're actually talking about. Because when scientists say empty, they don't mean like an empty room. They don't even mean like the vacuum of outer space between Earth and the Moon. The AIR you're breathing right now contains roughly 25 trillion molecules per cubic meter. The best vacuum humans have ever created inside the Large Hadron Collider at CERN in Switzerland still contains around 100 million particles per cubic meter. Even the space between stars in our Milky Way galaxy has about 1 million atoms per cubic meter. The deep interior of a cosmic void? About 0.01 atoms per cubic meter. That's roughly a billion times emptier than the best vacuum on Earth. You could scoop up a volume of space the size of a house and find maybe 1 or 2 hydrogen atoms floating around in it. Maybe. These voids aren't small either. A typical cosmic void stretches anywhere from 30 to 300 million light years across. The largest ones blow past 1 billion light years. And between these vast, empty regions, matter is squeezed into thin walls and thread-like filaments of galaxies, forming something scientists call the cosmic web. Think of it like a giant sponge. The holes in the sponge are the voids. The material of the sponge, those thin walls and threads, that's where all the galaxies, stars, and planets live. We exist on the membrane of a cosmic bubble, and almost everything around us is just empty. But nobody knew any of this until, surprisingly, recently. In 2019, a team of 4 astronomers at the University of Michigan changed everything. Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman were conducting a galaxy survey, measuring the distances to 133 galaxies in a patch of sky within the constellation Boötes. They expected to find galaxies distributed more or less evenly at various distances. Instead, they found a massive hole, a massive gap where galaxies should have been, but weren't. Out of 133 galaxies they measured, only 1 appeared in a distance range where dozens were expected. Their paper, published in the Astrophysical Journal in September 2019, carried a wonderfully cautious title, "A Million Cubic Megaparsec Void in Boötes?" Note the question mark. They could barely believe what they were seeing. A follow-up survey in 1987 confirmed it. They measured 240 bright galaxies across the region, and not a single one appeared in the distance range where 31 should have been. The Boötes Void was real, and it was enormous. About 330 million light-years across, centered roughly 700 million light-years from Earth. To put that scale into perspective, at the speed of light, the fastest anything can travel in this universe, crossing the Boötes Void would take 330 million years. At the speed of the Parker Solar Probe, the fastest spacecraft humans have ever built, it would take roughly 500 trillion years. That's about 36,000 times the current age of the entire universe, just to cross one void. But the really creepy part is what's inside it, or rather, what isn't. Over the following decade, astronomers kept searching. In 1987, they found 8 emission line galaxies inside. By 1989, they'd added 15 more. By 1997, using data from the IRAS satellite, astronomer Greg Aldering at Lawrence Berkeley National Laboratory brought the total to about 60 galaxies. 60! In a region of space where roughly 2,000 should exist. That's about 3% of what you'd expect. And those 60 galaxies aren't even scattered randomly. They form a strange tube-shaped filament running through the void's center, like a seam left behind when smaller voids merge together. Aldering came up with one of the most haunting quotes in all of astronomy. He said that if the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Think about that. No constellations, no Milky Way band stretching across the night sky, no visible stars beyond our own sun, just planets against an endless pure black canvas. Humanity would have spent most of its history believing it was completely, utterly alone in the universe, and the Boötes Void was only the beginning. 5 years after Kirshner's team found their giant hole in Boötes, the real bombshell dropped. In 1986, 3 astronomers at the Harvard-Smithsonian Center for Astrophysics published a paper that fundamentally changed how we understand the structure of the universe. Margaret Geller, John Hucra, and Valerie de Lapparente had been conducting the CFA Redshift Survey, mapping the three-dimensional positions of galaxies in a slice of the sky. When they plotted the data, what appeared on screen was astonishing. Galaxies weren't distributed randomly. They weren't even distributed in a vaguely uniform way. They clustered on thin walls and filaments surrounding enormous empty bubbles. De Lapparente later recalled how striking it was. The voids were circular, the walls separating them were sharp and thin, and the whole thing looked like a cross-section of a giant foam. Margaret Geller coined the term soap bubble universe, because that's exactly what it looked like. Galaxies clinging to the surfaces of invisible cosmic bubbles spanning millions of light years. Today, we've mapped this structure in incredible detail. The cosmic web consists of 4 components: nodes, which are massive galaxy clusters sitting at the intersections of filaments. Filaments themselves, long thread-like structures of galaxies and dark matter stretching 50 to 260 million light years. Walls, the flat sheets of galaxies at roughly average density. And voids, the vast empty regions that everything else surrounds. Simulations like the Millennium simulation, led by Volker Springel at the Max Planck Institute in 2005, traced 10 billion dark matter particles in a cube 2 billion light-years on a side. More recent simulations like Millennium TNG used 160 billion resolution elements on 122,880 processor cores, and every single one of them produces the same result: a universe dominated by emptiness, with matter clinging to thin walls like soap residue on the sides of a cosmic bathtub. But the cosmic web wasn't just interesting, it was about to reveal something deeply strange. In 2004, a Spanish physicist named Patricio Villalba was analyzing data from the WMAP satellite, which had mapped the cosmic microwave background, the oldest light in the universe, dating back to about 380,000 years after the Big Bang. The CMB is remarkably uniform. It's 2.725 Kelvin everywhere you look, with tiny variations of just millionths of a degree. But Villalba found something that shouldn't have been there. A region in the constellation Eridanus, spanning about 5 degrees of sky, that was roughly 70 millionths of a degree cold than average. At its center, the deficit reached 150 millionths of a degree. That might sound tiny, but typical CMB fluctuations run about 18 millionths of a degree. This cold spot was massive, both in angular size and in how far it deviated from normal. Statistical analysis showed there was only about 1 to 2% chance of a spot like this appearing randomly. The Planck satellite confirmed it in 2013. This wasn't a WMAP glitch. The cold spot was real, and nobody could explain it. Then in 2015, astronomer Istvan Saputty at the University of Hawaii's Institute for Astronomy found something jaw-dropping. Using data from NASA's WISE satellite and Hawaii's Pan-STARRS 1 telescope, his team discovered a supervoid aligned with the cold spot. This void stretches roughly 1.8 billion light-years across, making it one of the single largest structures ever identified by humanity. Saputty's paper, published in the monthly notices of the Royal Astronomical Society, described a region centered about 3 billion light-years from Earth that contains approximately 30% less matter than surrounding space. The Dark Energy Survey confirmed it in 2021 using gravitational lensing mass maps, detecting the supervoid at over 5 sigma significance. The idea was that this enormous void might be causing the cold spot through something called the integrated Sachs-Wolf effect. When ancient CMB photons travel through a void, they lose energy climbing into the gravitational well, and normally they'd gain it back climbing out. But because dark energy is accelerating the universe's expansion, the void stretches while the photons are inside it. The gravitational hill flattens out, photons exit with less energy than they entered, and they appear slightly colder. It's an elegant explanation. There's just one problem: the math doesn't work. In standard cosmology, the supervoid can only account for 10 to 20% of the cold spot's temperature deficit. Researchers at Durham University calculated it might produce as little as 9/millionths of a degree of cooling when the observed deficit is 150. Something else is going on, and the alternative explanations get wild. One possibility proposed by physicists, including Neil Turok at Cambridge, is a cosmic texture. These are defects in the vacuum structure of space left over from phase transitions in the early universe, similar to how ice crystals misalign when water freezes. Bayesian analysis found this was actually the most probable explanation at the time, but the most provocative theory came from Laura Mersini-Houghton, a theoretical physicist at the University of North Carolina at Chapel Hill. Starting in 2005, she proposed that the cold spot is the imprint of another universe pressing against the edge of our own. A bruise from quantum entanglement between our universe and a neighboring one in the string theory multiverse, stamped into our CMB before cosmic inflation separated them forever. Is there evidence for this? Not enough to convince most physicists. A 2023 analysis of Planck data found no evidence supporting her specific predictions. But the cold spot remains unexplained. And as Tom Shanks at Durham University noted, if certain polarization signals are found, a collision with another universe would become a serious hypothesis. Now, if you're finding this useful, hit subscribe. I cover space and science stories like this regularly, because this next part is where things get personal. In 2013, 3 astronomers published a paper in the Astrophysical Journal that might fundamentally change our understanding of where we sit in the universe. Ryan Keenan at the Academia Sinica Institute of Astronomy and Astrophysics in Taiwan, Amy Barger at the University of Wisconsin-Madison, and Lennox Cowie, a fellow of the Royal Society at the University of Hawaii, presented evidence that our entire region of the universe, the Milky Way, the Local Group, most of the Laniakea supercluster, sits inside a massive cosmic void. The KBC Void, named after their initials, stretches roughly 2 billion light-years across. That's about 7 times larger than the average cosmic void. And our galaxy appears to be within a few hundred million light-years of its center. Evidence comes from multiple sources. Near-infrared galaxy counts, optical surveys, and X-ray cluster data all show the same thing. The region of space around us, out to about 1 billion light-years in every direction, contains significantly less matter than the cosmic average. Estimates range from 20 to 50% below the mean density. Now, here's why this matters beyond just being a cool fact. There's a crisis happening in cosmology right now, and the KBC Void might be the answer. It's called the Hubble tension, and it's one of the biggest unsolved problems in physics. When astronomers measure how fast the universe is expanding using nearby objects like supernovae and Cepheid variable stars, they get a number of about 73 kilometers per second per megaparsec. That's the SHOES team result from 2022. But when they measure the same thing using the cosmic microwave background and the standard model of cosmology, they get about 67.4 kilometers per second per megaparsec. That's the Planck satellite result. The difference is roughly 9%. And it's not a measurement error. The discrepancy has reached a significance of 5 sigma, meaning there's less than 1 in 3.5 million chance it's a statistical fluke. Something is wrong with our understanding of the universe. Either our physics is broken or something about our local environment is fooling us. The KBC Void offers a surprisingly elegant explanation. If we're sitting inside a giant underdense region, galaxies inside the void experience an outward pull from the denser matter surrounding them. This creates peculiar velocity outflows, galaxies moving outward toward the void's walls, faster than cosmic expansion alone would predict. These outflows inflate the measured redshifts of nearby galaxies, making space appear to expand faster locally than it actually does on a global scale. Physicist Indranil Banik at the University of Portsmouth explains it by comparing a supervoid to a homogeneous universe with some concentrated negative mass added in. This creates a repulsive gravitational effect that boosts nearby redshifts beyond what cosmic expansion alone produces. The numbers check out too. The KBC Void model predicts local expansion should exceed the background rate by about 11%. The observed Hubble tension is about 9%. That's remarkably close. And in 2025, the evidence got a lot stronger. Banik and his colleague Kalaitzidis published results in the monthly notices of the Royal Astronomical Society testing the void hypothesis against 20 years of baryon acoustic oscillation data. They found that a void model is 100 million times more likely than a void-free model consistent with Planck cosmology. The void-free model showed a 3.3 sigma tension with the data, while void models showed only 1.1 to 1.4 sigma. The BAO data showed a systematic discrepancy that grows with decreasing redshift, exactly what you'd expect if we're inside a local underdensity. As Banik put it at the 2025 National Astronomy meeting in Durham, by now it's pretty clear that we are in a significant underdensity. If this is confirmed, it means humanity spent centuries assuming we occupy a perfectly average patch of the cosmos, and it turns out we were sitting in one of the emptiest places in our cosmic neighborhood the entire time. But to really understand why voids are terrifying, you need to understand how they form and what they're doing right now. The seeds of every cosmic void were planted in the first fraction of a second after the Big Bang, roughly 13.8 billion years ago. During cosmic inflation, the universe expanded by a factor of at least 10 to the 26th in a fraction of a second. And as it did, tiny quantum fluctuations in the density of matter and energy were stretched to macroscopic scales. As Scientific American describes, these microscopic quantum blips lost the ability to disappear back into the vacuum haze and froze into permanent existence. These frozen density ripples became the blueprint for everything. Regions that were slightly denser expanded more slowly, pulling in more matter through gravity, eventually forming the filaments and galaxy clusters of the cosmic web. Regions that were slightly less dense expanded faster, losing matter to their denser neighbors, hollowing out into what would become void. Dark matter, which makes up 85% of all matter, provided the gravitational scaffolding. Where dark matter was abundant, galaxies formed. Where it was scarce, voids grew. Over billions of years, smaller voids merged into larger ones. Researchers Scheth and von de Weygart described this process in 2004 as a void hierarchy. Small voids embedded in larger underdense regions coalesce, the thin walls between them squeezed away, producing ever bigger voids over time. It's like soap bubbles merging on a window, the membranes between them dissolving until fewer, larger bubbles remain. And this is where it gets genuinely frightening, because the voids aren't done growing, they're accelerating. Inside a void, there is so little matter that gravity essentially loses the fight against dark energy. Dark energy, the mysterious force driving the universe's accelerating expansion, dominates inside voids earlier and more completely than anywhere else in the cosmos. As Harvard astrophysicist Avi Loeb describes it, voids are dominated by the repulsive gravity of dark energy, and the walls of their expanding bubbles tend to collide and coalesce, making even bigger voids over time. In dense regions, inside galaxies, star systems, galaxy clusters, gravitational attraction still overwhelms dark energy. But in the voids, dark energy is the sole dominant force, pushing everything apart, unchecked. This is why scientists are increasingly using voids as laboratories for studying dark energy. A 2020 study led by Nadather at the University of Portsmouth combined void measurements with baryon acoustic oscillations and produced what the researchers called the most precise tests of dark energy and cosmic expansion to date, more precise than traditional supernova methods. And the results keep coming. In April 2024, the Dark Energy Spectroscopic Instrument, or DESI, released the most precise measurement ever of the universe's expansion history. Among their findings were hints that dark energy itself may be changing over time, strengthening at a significance of 2.5 to 3.9 sigma. In October 2024, DESI released a dedicated void catalog of 1,461 voids from their Year 1 data. Meanwhile, the European Space Agency's Euclid telescope, launched in July 2023, detected 26 million galaxies in just its first week of science operations. Its Void Working Group has about 100 scientists devoted specifically to studying these empty regions. We're entering an era where the nothing between galaxies might tell us more about the nature of reality than the galaxies themselves. And that leads to the most uncomfortable realization of all. Voids currently make up about 80% of the universe's volume, and that fraction is increasing. As dark energy drives accelerated expansion, voids grow, merge, and claim more cosmic territory. The cosmic web, that beautiful sponge-like structure connecting galaxies across billions of light years, is being slowly dissolved. Voids aren't just the emptiest places in the universe, they are the future of the universe, a literal preview of what everything, everywhere will eventually look like. The timeline is staggering. Within the next 100 billion years, every galaxy beyond our local group, few hundred trillion years, the last stars will burn out as galaxies exhaust their hydrogen fuel. Within 10 to the 20th years, remaining stellar remnants will fall into supermassive black holes. Within 10 to the 100th years, even those black holes will evaporate through Hawking radiation, and after that, the universe becomes what physicists call heat death. A near-perfect vacuum, where particles are so far apart they rarely interact. Every point in space becomes a void, the cosmic web fully dissolved. The temperature of everything, everywhere, asymptotically approaching absolute zero forever. That's what a void looks like from the inside, and it's where everything is headed. Avi Loeb wrote something about this that stuck with us. He said that for observers lucky enough to be born inside a void, life must be boring. There are no nearby intergalactic hubs to meet aliens because matter is rarefied. Being born in a void, he said, can trigger melancholy. There is no escape from this sense of loneliness. 40 years ago, humanity didn't even know cosmic voids existed. Today we have mapped thousands of them, discovered that we likely live inside one, and realized they may hold the key to the greatest unsolved mystery in cosmology. Instruments like DZ, Euclid, and the upcoming Nancy Grace Roman Space Telescope are about to increase our void catalog from around 6,000 to potentially hundreds of thousands. The emptiest places in the universe aren't hiding from us anymore. They're revealing something about the nature of dark energy, the structure of the cosmos, and the fate of everything that exists. And maybe the most terrifying part isn't the voids themselves, it's that they're patient. They've been growing since the beginning of time, and they'll be the last thing standing when everything else is gone. If you want to see another story about the strangest things hiding in the cosmos, click the video on screen now. Subscribe so you don't miss the next one.